All right, my friends, welcome. Let us go with our part 2. So we did instantaneous rate of change with graphs. Now, what if I want to find the instantaneous rate of change when I give you an equation, right? Just like we did in the previous video with average rate of change, we did graphs and then equations. So now we'll do instant graphs, now equations. So when we did average rate of change, right? Average rate of change was rise over run, right? Well, instant slope is still the same idea, but we don't want to use the same notation for average rate of change and instant. So just so you know, from now on, when we're talking about instant rate of change, we use something called dy over dx. This is just a way for us to know that we're talking about instant and not average rate of change, all right? So that's why if you look over here, it says determine the derivative. Now, derivative, let me just explain. The derivative is going to give us the function that gives us the instant slope. That may sound strange, but just bear with me while we kind of get some practice and we'll make sense of this. So let us start, maybe, I want to start us with a problem like this right here, okay? So the derivative gives you the function that provides you the instantaneous rate of change. Now that may seem all wordy, but let's begin. So let's say determine the derivative of the function below, and I should say and evaluate when x is equal to 2. So let's say my equation is y equals 4. Okay, so we have y is equal to 4. I want to find the instant speed. All right, so I want to find the instant speed at x equals 2. Well, in order to do that, I need to take what's called the derivative. To find that, we do dy dx, just means instant rise over instant run, instant slope. Okay, well, look at this graph. Well, we already talked about it. It's a horizontal line. If you pick any one point on this graph, well, what's the slope of a straight line? Well, if you look at the previous videos, the slope of this, the instant slope, no matter what you choose, it's 0 because it doesn't have a change in y. So this would be 0. We'd have a slope of 0, my friends. And we really wouldn't have to worry about anything else because, again, in this scenario, we don't have a change in y. Let's go ahead and look at a different example problem. Okay, let's take a look at this one. Determine the derivative of the function and determine the instant rate of change at x equals 2. So at x is equal to 2, right here, I want to find my instant rate of change, the actual line that crosses through this boundary point just once, okay? Well, let me show you a technique. This is called the power rule. So we have y is equal to x squared. In order to take the derivative so that we can get the instant slope, believe it or not, all you have to do is you just bring the 2 down. What's the invisible number in front of the x? Let me write it over here. Well, there's like an invisible 1 here. So you take the 2 and multiply it with whatever number's here. Well, 1, 2 times 1 is 2. So you just get 2x. So pretty much you just bring the 2 down, or whatever the exponent is, and then you subtract the exponent by 1. Okay, this is a little trick, and we're going to learn where this trick comes from after the AP exam, which is just 1. So in other words, my derivative function is 2x. Well, what is that? What does this mean? Well, this is going to tell me whatever x value I plug in, it will give me the instant slope of anywhere on this curve here. Pretty nifty stuff. So let's plug in 2. So we know this is 2x. So let's do dy dx is equal to 2 times 2. Plug that in and we get 4. What does this mean? Well, that means that my instant slope at x equals 2 is 4. In other words, 4 over 1. And watch this. This is how crazy it is. You just go up 4 over 1. 1, 2, 3, 4 over 1 right there. And 1, 2, 3, 4 over 1. And now I can connect these 2 points. There it is, my friends. The instant speed at that point. And you can see it creates this line right there. Okay, just by following the slope, you can get it. That's it. Pretty crazy stuff. This little trick that I just showed you will always work. So let's look at the exact same graph. The exact same graph, but at a different point at -1. Okay, so at -1, it's right here. Okay, well, I want to determine the derivative, which means I want to get the function that'll give me the instant speed. Well, again, the trick is like this. Okay, y is equal to x squared. Well, dy dx to determine the instant speed or derivative, you bring the 2 down, and then you subtract by 1, and you just get 1. So dy dx is equal to 2x. We just did that problem up above. Let me change colors now. So, well, I want to find my instant speed at -1. Again, this will work. You can plug in whatever. So 2, let me get rid of that, is equal to, now go ahead and plug in -1. So 2 times -1, which is -2. So what does that mean? Well, that means that my instant speed, my instant rate of change at that point is -2, or in other words, -2 over 1. Well, look, does that make sense? I go down 2 over 1, and I can do the same thing, and there it is, and it's negative. That makes sense, and it crosses through that point exactly. Okay, well, we already talked about this. Well, let me get rid of that line. Okay, where on this graph do you have 0 slope? Well, right there at 0, right? It's 0. Well, does it make sense? If I plug this into my equation, will I get 0? Well, let's try it. dy dx is equal to 2 times 0. Well, that's 0. That means my true. All right, maybe let's go through another problem here that's a little more challenging. X to the third. I want to find the instant slope at -1, which is pretty much this right here at -1. Well, you could tell it should be positive, so we better get it to be positive. Okay, and let's see if we can get that. Well, how do we do this? Well, we do the exact same thing that we did, okay? And really, it's just a simple trick, and this works for any equation that you try. You bring the 3 down, so you'll just get 3x, and then you subtract 1. That's it, and you get squared. So my derivative function is 3x squared. Now if I plug in any point, it'll tell me the instant slope at that point. Check this out. 3 times -1 squared. This is 3 times 1, which is 3. That means my instant slope at -1 is 3. Or in other words, 3 over 1. Well, let's check it out. Go over here, go up 3. 1, 2, 3 over 1. 1, 2, 3 over 1. There it is, my friends. The equation that touches the boundary at -1, and we can use that slope to write this equation, which is right there. And that is our instant slope at that point, and the derivative tells us the equation that'll give us that. So maybe let's take a look at maybe just some more problems, just for the fun of it. All right, so let's go ahead and look over here at y is equal to 2x. Okay, well, let's go over here. We have y equals 2x. Well, it's like an invisible 1 up here, right? Well, what do? We're going to take the derivative. So you bring the 1 down. So this is just 1 times 2, which is 2x to the subtract 1, and you get 0. Well, what's anything raised to 0? Well, it's just 1. So we get, dy dx is equal to 2. If you're not sure about this, you can actually verify this. Okay. I'll do a quick example here. You can just fast forward if you already understand this. 2 to the third is 8. 2 to the, hold on real quick. Okay, let's just make 3 columns really fast. Okay, 2 to the third is 8. 2 squared is 4. 2 to the 1 is 2. Okay. Well, what do you notice the pattern as we go through here? Well, you'll notice what's 8 divided by 2? That's 4. What's 4 divided by 2? That's 2. 2 divided by 2 is 1. So anything raised to the 0 is 1, because essentially you're just taking 2 and dividing it by itself. So there it is. So if you go at x equals 4, well, my friends, it's just up to over 1, down to over 1, and you essentially get on this line because it's a straight line. The instant rate is just 2 anywhere along this line because it's that actual straight line. All right. Let's take a look at maybe a more complicated one here. Determine the derivative of the function at x is equal to 3, and evaluate it. So first things first, in order to do a problem like this, well, how we want to do these is we want to look at them individually. So let's go dy dx is equal to, well, ignore everything else and look at x to the third. Well, bring the 3 down. So this is 3x, and then subtract 1. So 3x squared, plus bring the 2 down. Bring the 2 down and then subtract 1. So it's going to be 2x to the 1, or you don't have to write it. Well, we just saw in the previous video up above, negative 9x. Well, this is 1, and we're going to end up subtracting by, bring the 1 down, and then subtract the 1, and we get 0, which will disappear. So we just get negative 9. Okay. And what's the derivative of just a number? A straight line, right? This is just a straight line at negative 9. Well, that's 0. So this is gone. And this right here is my function that'll give me my instant slope. So I can write it now. 3x squared plus 2x minus 9. All right. Now I can plug in 3 into this equation, and I should be good to go and find my instant slope. I'm going to get 3 times 9 plus 6 minus 9, 27 plus 6, 27, 28, 29, 30, 31, 32, 33, minus 9, I get 24. So dy dx is equal to 24, or 24 over 1. So that means that x equals 3. That means that I have to go up 24 and then over 1. And you can see that would be kind of hard to do, but nonetheless we could still use our equation to do that and not have to always rely on a graph. All right, so let's go ahead and just take a look at a few more here. We're just gonna do 4 of these, okay? And let's just get really good at these problems. So when we do derivatives, okay, I showed you we do y equals, we can do dy dx to refer to trying to find the instant slope. Well, in calculus, there's 3 different ways, and it's really up to the teacher. So we're going to learn all 3 different ways. You can do y and then dy dx. This is my favorite because I can visually see instant rise over instant run. You know, your instant rate of change. It's a real clear what you're looking for. Another way to write this is y prime, and it just means take the derivative. They mean the exact same thing, okay? Now, what if you're in function notation? F of x. Well, this is why the prime came about, because, well, let's just write it as f prime, and that means derivative. That means instant rate of change. So let's go over here. Determine the derivative of the function below. Well, y is equal to 5. Well, this will be dy over dx, right? Our instant rate of change. Well, it's just 5. So if you were to graph this, it's just a straight line. Again, this doesn't have any rise over run or any instant rise over run. So it's just 0. Let's go to this next one. Or you could write this as y prime is equal to 0. I'm just showing you 2 different ways here. F prime of x is equal to, well, bring the 18 down. 5 times 18 is 60. I do believe so. Let me just, I got a calculator right here. All right. Just, I don't trust myself right now. 90. I knew it. Okay. 90 x to the, subtract 1, and you get 17. And that's it. Let's take a look at this one here. Y prime or dy dx. Well, bring the 5 down. This is 20 x to the 4th plus, well, there's like an invisible 1 in front of the x, right? And you notice when we take the derivative of just x, the x disappears, so we're just left with 1. Again, you can rewrite this as dy dx is equal to 20 x to the 4 plus 1. Let's try this one over here. F prime of x is equal to, well, bring the 4 down. 4 times 4 is 16 x to the minus 1, and that's 3. Well, over here, what will this become? Well, it has an x variable, and it'll disappear, right? Because it's x to the 1. Bring the 1 down, and then we subtract 1, and we'll get x to the 0. Anything to the 0 is 1. So we'll get negative 5. And just like before, right? Any number, when you take the derivative, it's just 0. So what's the derivative of negative 3? Well, it's just a number. So it's 0. So gone. And there it is. So that's 4 problems. Taking derivatives. This is finding